Start. Seat take this. Seat take.
Welcome to the last day session of the GIAN course MHPDIMG 2024 conducted by the Department of Electrical and Electronics Engineering, National Institute of Technology, Rourkela. The present session will be handled by Professor Monalisa Pattnaik and her PhD scholar Pradyumna Kumar Behera. Let me introduce Mr. Pradyumna Kumar Behera to you all. Mr. Pradyumna Kumar Behera received M.Tech degree in Electrical Engineering from Veer Surendra Sai University of Technology, Burla, Odisha, Odisha, India in 2016. He is presently pursuing his PhD degree in Electrical Engineering at National Institute of Technology, Rourkela, India. His areas of research interest include design of power electronic converters, renewable energy systems, hybrid energy storage systems, electric vehicle charging infrastructure and power management of DC microgrid. Now the lab session will be handled by Mr. Pradyumna Kumar Behera. Sir, please.
Okay, before Pradyumna starts, good morning all. Today, as already I have introduced this today's session in my last class. So we are going to discuss about the DC microgrid and the PV and battery based system will be integrated to the DC microgrid. So that will be explained by in detail by my student Pradyumna Kumar Behera. So he is just going, before he starts, you can check the previous slides. Already the photo you have seen, but now in live you can check all the details and you can ask your questions after the end of this session. Thank you.
Good morning all. I am Pradyumna Kumar Behera, research scholar under the guidance of Dr. Monalisa Pattnaik. The topic of the presentation is power management in a DC microgrid and its demonstration. So the learning objectives are basically, we will be discussing the architecture of a photovoltaic system equipped with an actively configured battery supercapacitor based hybrid energy storage system. We will try to address and solve the various power balance issues arising during dynamic condition in a DC microgrid comprising PV as the primary energy source and hybrid energy storage system and load. We will look into the development of the test bench and controller implementation of a PV-fed LVDC microgrid equipped with hybrid energy storage system in real-time digital platform during different operating conditions. So you can see the architecture of the PV-based LVDC microgrid with hybrid energy storage system. You can see that the PV panel is interfaced to the DC bus through a buck converter. The buck converter is utilized here to perform the MPPT operation. And here we can see that we have two different bidirectional converters. The configuration is same, but they are connected in actively configured fashion, and it is used for the charge and discharge control of the battery and supercapacitor. So various control schemes associated with the PV-based LVDC microgrid is, first we were having the maximum power point tracking control. In this you can see we are having a PV-fed standalone system in which a PV module is connected to the load through a buck converter, and we are using buck converter as an interface in between the PV module and the load. Basically, in case of maximum power point tracking control, the important is the load matching between the source and the load. So basically you can see that the relationship between the input variables and output variables of the buck converter during steady state is represented by equation number 1. The important point is that the load impedance that is getting reflected at the input side of the converter is given by equation number 3. So if you can see that the relation of the internal impedance with respect to there is a relation with respect to the duty. So by adjusting the duty ratio, the internal resistance is valid such that it should be equal to the characteristic impedance of the PV module under a certain operating scenario. This is the flowchart of the pattern of the MPPT method. Already most of the people are acquainted with this one. It is used to track the maximum power from a PV panel. You can see that I have marked 4 operating points M, N, O and P. At the peak of this PV curve, you can see the slope is 0 actually. This is the point at which maximum power point is present. And based on the scenario, we can see that whether the operating point is moving in the upward slope or it is moving in the downward slope. Accordingly, we have to determine the maximum power point. Next is the filtration based control of hybrid energy storage system. Basically, the power balance equation is represented using the equation number 4. You can observe that the PV power minus the load power and the loss power should be equal to what it should be consumed or delivered by the battery and the supercapacitor. However, battery is only going to deliver the average power demand or the steady state demand of the load, while the supercapacitor will be acting during the transient period. So here you can see what we are doing for controlling the DC bus voltage. The DC bus reference voltage in our case is 48 volt and it is compared with the actual DC bus voltage of the plant, and the error is processed through a PI controller. The output of the PI controller will generate the total reference current required to maintain the DC bus voltage. This INET reference is the total reference current generated from the when the error is processed through the PI controller. It is getting segregated into 2 components through a low pass filter, and the steady component or the average component is provided to the battery controller, and the other component is given to the supercapacitor. So in this control strategy, we can see that the LPF splits the total reference current into 2 different components. One is the high frequency component and other one is the average component. And for selecting the cutoff frequency of the this low pass filter, you have to perform some test during load change condition as well as irradiation change condition, or you can follow the Ragan chart, and according to that you can according to the time constant of the battery and supercapacitor you can determine this cutoff frequency of the low pass filter. Next, we will discuss about the development of the PV hybrid energy storage based LVDC microgrid system. Here you can see the orange zone over here is basically the plant. Here we have the PV panel, battery and supercapacitor connected through different converters. The PV panel is interfaced through the DC bus through a buck converter. The battery and supercapacitor are interfaced using the bidirectional converter. All the signals are sensed. The voltage of the PV panel, the current of the PV panel, and the battery current, supercapacitor current, DC bus voltage, all are sensed using the sensor circuits, and after signal condition they are sent to the ADC channel of the D-Space DS1103 digital controller. And here you can see this D-Space CPU is connected with our host PC, and it is also connected through a D-Space CLP1103 interface. In this CLP1103 interface, we have 20 numbers of ADC channels, 8 numbers of DAC channels. We have a master PPC board, we have a slave IO board for generating the PWM pulse, and in our host PC, we are basically implementing the MPPT controller, we are implementing the power management, and also in the host PC we have another software that is basically your D-Space DS1103 control test 5.6, which is basically used for experimenting, visualizing, and data monitoring, data recording, storing and plotting are done in the control test 5.6. Here I have shown you the the parameters of the PV panel. The maximum power is 600 watt at 1000 watt per meter square and 25 degrees Celsius. The open circuit voltage is 90 volts. The short circuit current is 9 ampere, and the rated voltage or the maximum power point voltage is 75 volt, and the current at the maximum power point is 8 ampere. The buck converter connected to the PV panel is having a specification. The inductor value is 1 millihenry. The input capacitor you can see is a 220 microfarad. The output capacitor is 470 microfarad. And the switching frequency considered for this case is 10 kilowatt. Similarly, I have shown you the various specification of the hybrid energy storage system. We have considered two number of battery packs, lead acid battery pack having individual voltage of 12 volt, and the inductor value is 0.5 millihenry, and we have connected a supercapacitor pack having a voltage of 16.2. We have connected two numbers of supercapacitor voltage, so the rated voltage is going to 32.4 volt, and the inductor for the supercapacitor energy storage system is also 0.5 millihenry, and the switching frequency of the bidirectional converter is considered same as that of the buck converter, that is the 10 kHz only. So next I am going to discuss about the design and calibration of sensors. We are using the LEM make LA55P current sensor. This current sensor is having a maximum current measurement of 50 ampere. Okay. Now what we are trying to do, this current transducer is developed in such a manner, we have connected in the test rig in such a manner. So we want to scale the 10 ampere current to 5 volt. Let's say you can see that the current transducer is developed in the developed test rig to scale down the current of from 10 plus 10 plus minus 10 ampere to plus minus 5 volt. So basically we have to select the number of primary turns in such a manner that the button resistor connected at the output of the measurement port of the current sensor should fall in the range of 50 to 160 ohm. This is actually specified in the data sheet of this current sensor, and further the maximum number of turns NP is also decided by the maximum value of current. As we know that this current is having a maximum current measurement of 50 ampere. So what I am doing, I am trying to scale my 10 ampere to 5 volt. So what I will do, I will first of all I will find out the number of turns that is required. So 50 divided by 10, the number of turns should be less than or equal to 5 actually. So here I have mentioned that where NP can be 1, 2, 3, 4 or 5. Now this particular current transducer exhibits a conversion ratio of 1:1000. So I have considered 5 number of turns. I am considering the number of turns as 5, and you can see that for my measuring current is 10 ampere. So then I have to calculate the output current. For this you have to use this formula. So what you have to do, you have to just multiply the measuring current value, this is 10 into 5, by the current transducer ratio. You are getting a current of 0.05 ampere. Now for an input current of 10 ampere, the output measuring resistance or the button resistance to acquire a 5 volt at the output is calculated using this formula. You can see that it is 5 by 0.05. We are getting a value of 100 volt. So this value, the button resistor value, I have to connect 100 ohm. In the similar manner, if you are not having a 100 ohm resistor, let's say you are having a resistor of, let's say, 110 ohm. So in the reverse manner also you can follow, and you can change the number of turns. I can show you I can tell you one instance. If you want to measure the maximum current of 25 ampere, then you have to use the number of turns to be 2. Then you can use the button resistance as 100 ohm. So there are some important points you should note while selecting the output resistors. See, the output resistor or the button resistor should not be selected beyond 150 ohm. As the data sheet is specifying that you can connect any resistor in between 50 to 160 ohm, but actually from my observation, what I have seen that if I am going beyond 150 ohm, so I am getting non-linearity in the measurement reading. And as low as possible, the tolerance value of the button resistance should be selected. The tolerance value of the button resistance actually should be selected in 1% range. If you are getting a lower tolerance value of resistance also, then it will be very good actually. Further, in order to increase the accuracy in the measurement and to reduce the effect of temperature on the button resistor, we are not using a quarter watt resistor, but instead we are going for a half watt or 1 watt resistor. That is very important. That is one of my observation. Now I am going to discuss about the design and calibration of voltage sensor. So let's say for this instant we have considered a source voltage of 200 volt and it is required to be downscaled to plus minus 5 volt. And this particular transducer has a measuring voltage of, it can measure a voltage in between 10 to 500 and it operates at a plus minus 15 volt supply. Similar is the case for the LEM LA55 sensor also. It operates in the range of plus minus. The power supply requirement is plus 15 as well as minus 15. And the manufacturer data, if you go through, you can find that the primary side current is 10 milliampere. So as we are seeing that the primary side current that should be entering this voltage transducer is 10 milliampere. So we have to connect one source resistance RI. Source resistance we have to connect and we have to select the source resistance very carefully because this current should not exceed 10 milliampere. And also this LV25P current sensor exhibits a conversion ratio of 2500:1000. So in this case, first of all we have to find out the primary current. How we will determine the primary current? Obviously we have the source voltage that is connected to your plant. It may be 200 volt or for some other person it may be 400, for some other person it may be 100 volt or for some other person it may be 500 volt. So first of all you have to calculate this current, the primary current, and you should keep in mind that it should not go beyond 10 milliampere. So what we are getting over here, what I am doing, I have connected a 20 kilo ohm resistor. So 200 by 20 kilo ohm resistor I am getting what? 10 milliampere current. So I have taken the maximum value, I have kept the maximum value for easier calculation. Now for calculating the button resistor, the data sheet is specifying that you should select the input resistance. This input resistance RI should be selected in such a manner that the button resistor or the output resistor should fall in the range of 100 to 350 ohm. Right? So in this case what you have to do, so the first what we are doing, first of all we are calculating the power dissipated. Power dissipation we are calculating while selecting the input resistance. First of all we will be finding out the power, how much power it will be dissipated. So for power you can V square by R you can see that I am getting a 2. So while selecting the input resistor, you have to select the input resistor in such a manner that the power rating of the resistor or the input resistor is more than this 2 watt. So usually we are going for 3 watt, 4 watt, 5 watt, sometimes we are going for 8 watt also. So why it is required? Because otherwise there may be a chance due to overheating, there may be failure of this input resistor. So there are some important points. Again, in order to avoid the nonlinearity in the measurement reading, we should not go beyond 300. This is one of my observations, and the low tolerance value of the output resistor should be selected. And again, the button resistance value, in order to increase the accuracy in measurement and to reduce the effective temperature change, half watt or 1 watt power rating resistor should be selected actually. Next I will be discussing about the IGBT or the MOSFET driver. We are using the TLP350 optocoupler based IGBT and MOSFET driver. It is very popular choice for the gate driver application, and it basically provides the isolation between the input and the output port. You can see the input port and output ports are actually isolated. So it basically what it basically helps to protect the control circuitry from voltage spike and the noise. You can see that this side the ground is different and this side the ground is going to be different. So it is the input and the output side are completely isolated from each other. And this TLP350 actually comes with 8 LED dual-in package, and the input signal or the pulse that we are getting from any of the controller right? We will be, for this we are connecting a 320 ohm resistor, because the current sink for this TL50 is also very less. And it is very important to know that the input is reference to the signal ground or the control ground. This ground is the same ground as that of your controller. In our case it is the DSpace DS1103 digital controller, and which is separate from this power ground. This is actually the power ground. This is, both are isolated from each other. And here you can see the result. We are getting an input pulse from the DSpace DS1103. We are getting the switching frequency we have taken at 20 kHz. Here you can see that the peak to peak voltage is 3.44 volt, and the output voltage you can see the same 20 kHz pulse is coming, but here you can see we are getting a voltage of 15.8 volt. That is actually required to drive a MOSFET or IGBT actually. So these are some of the references which can be followed. And now I am going to show you the interface of the DSpace controller. So first of all, you have to turn on all your powers for your sensors, and DSpace power you have to turn on. You can see this one. This is our CLP1103 digital controller. Here you can observe. Here we have 20 numbers of ADC channels are there. Here we have 20 numbers of ADC channels. Here we have 8 number of DC channels. This slave IO, is, we are using this slave IO for getting out the PWM signals for our buck converter and bidirectional converters. Next, when we are opening the MATLAB, then already we have installed the DSpace platform with this system. So one pop-up will come. Here you can see that various selections will be given to you. So for our system, in this system we have connected the DSpace 1103 digital platform. So for this you have to select RTI 1103. If I select this RTI 1103, you can see that it will be configuring the DSpace software. For the MATLAB version, actually this DSpace DS1103 is compatible with the 2016A version. So you can see this, all the real-time interface to the Simulink and all these are getting activated, and you can see a message in the command window that the real-time implementation platform support is getting activated. Now it is completely activated. Next, in the command window, if you press, now I have shown you that the DSpace DS1103 is completely activated. So if you type command RTI and press enter, so you can see that we have a library of the DSpace DS1103 digital controller is going to open up. In that you can see various block sets are present, and we have the master PPC and the slave DSP F240. In the master PPC window, if you double click this one, you can get the various ADC and DAC channels, and also you can get different interfaces, and the encoder also you can get for if you are trying to measure the speed of a motor. You can use this encoder. Position encoder you can use. Similarly, if I go back and open the slave DSP F240, in this you can see we have got various PWM blocks you can get. This is PWM, this is DS1103SL DSP PWM. Other one we have DS1103SL DSP PWM3. This is basically we are using for the 3-phase pulse generation. This is we are using for generating pulse in case we are operating with the DC microgrid. And similarly, you can get different other different, if you want to do the space vector modulation also, you can get the block over here. Similarly, you can get some demo models also. If you go through if you double click the demo, you can get different demo models present over here related to different systems actually. If you are getting started with the system, then first of all you will be getting a demo model related to the spring mass damper system, and lot of examples are also present. So you can open it and you can visualize that one and learn from there. So now I will be discussing about the power management in the PV fed LVDC microgrid comprising of this hybrid energy storage system. Already I have modeled this one for saving the time. So I will show you what I have done. So first of all we have to sense the signal of the PV system. So we are sensing the voltage of the PV system, we are sensing the current of the PV system. So what we have done, we have connected the sensor output to the ADC channel, MUX ADC channel 6 and 7. So from here you can see I have selected 6 and 7. From 6 number channel I am using it to take my PV current, and I am using the MUX ADC converter 4. Converter 4, in that we have got two number of channels. One is the 13 and other one is the 14 channel. 14th number channel I am using it for getting my PV voltage. So in the similar manner, you can see that I have used different ADC channels. I have used the ADC channel 19 for measuring the DC bus voltage. I have used the ADC channel 18 for measuring the battery current. Similarly, I have used the converter 3, ADC converter 3, channel 9 and 10 for measuring the supercapacitor current, as well as for measuring the battery voltage supercapacitor. In the similar manner, what you can do is you have to connect all your sensor output to the ADC channel. And these blocks you can get from the library. Just now I have shown you the library, right? In that library you can get all these blocks. And after this you have to model your system, model your control algorithm. So for PV the input that is going is IPV and VPV. If I open this subsystem, you can see that here you can see I have connected two gains. This 10 is the D-space gain. Actually, whatever signal is coming through ADC channel, D-space automatically is going to scale it down by 10. So in order to get the same value, obviously I have to multiply the gain over here. Let's say I am measuring, I am getting a 5 ampere current, so it is going to come 0.5. So in order to get 5, again I have to multiply this D-space gain, and this one is the sensor gain. So for this case you can see if I am measuring, if I am taking the output as 10 volt and I want 10 ampere and I am scaling it to 5 volt, then the D-space gain is going to be 2. But for this case, for the PV system, I have used two number of turns. I have used, this one is the PV sensor. This one is the PV sensor. You can see that here I have used two number of turns, and therefore here the button resistor connected is 100 ohm. So this current sensor is capable of measuring maximum current of 25 ampere. So what I am doing, I am scaling the 25 ampere to 5 volt. So obviously what is the sensor gain? 25 by 5 is going to be the sensor gain. So the value comes to be 5. So in the system you can also, that's why I have used this gain sensor as 5. Similarly for VPV, I have used the sensor gain of 50. This is the voltage sensor. Voltage sensor, this side, it is measuring a voltage of, input voltage of 250 volt. It can, maximum voltage I have connected 250 volt, and the button resistor I have connected 100 ohm. So in that sense what I am doing, I am converting the 250 volt to 5 volt. So in this sense the gain, sensor gain becomes what? 50. So I have connected, you can see in the system, I have connected a gain of 50, and this 10 is the inherent gain of the DSpace DS1103 digital controller. Now all the outputs, and the output of this one is going to the MPPT block, and here we are doing the pattern one of the MPPT algorithm. Here we have written one code for this one actually. In the similar manner, this is for the PV MPPT system. In the similar manner, and the output of the PV MPPT will be a duty. This duty is going to the PWM channel. You can see over here, it is coming through this one, PWM channel, and the switching frequency of this PWM channel is selected as 10 kHz. This is all about the PV MPPT system. Now we will be discussing about the DC bus voltage regulation using the battery supercapacitor system. So for this one, this is our subsystem I have created. In this, all the inputs from the ADC channels are going, you can see. And this is the DC bus voltage, battery current, supercapacitor current, load current, battery voltage, and the supercapacitor voltage. Now already I have shown you this diagram of just now, the control diagram of the battery and supercapacitor based hybrid energy storage system. What we are doing for my system, what we have done, we have connected a 48 volt reference. We are taking the DC bus voltage and we are comparing it, and we are passing it through a PA controller. This one just now I have explained. You can see what I am getting a total reference current. This total reference current is, we are passing it through a low pass filter. This is the first order filter having a time constant of 0.2, and then from this we are getting the battery reference current. The battery reference current is going to be compared with the battery actual current, and it is again going to be passed through a PA controller in order to generate the duty cycle of the converter. And what we have done, the battery reference current is getting subtracted from the total reference current in order to get the supercapacitor reference current. So battery is going to deliver the steady state power, and the supercapacitor is going to deal with only transients. Transient means in case in the system the transient will occur during the load change period, and during the irradiation change time, these irradiations will be occurring. So what we have, this supercapacitor is going to deal during that period only. Otherwise, it will remain at the zero value. The current output of the supercapacitor is going to be zero during other periods. So after that, what we have to do? After you model the complete system using all the ADC blocks, and after modeling the control algorithm, you have to simply press Ctrl B, or you have to press this symbol. You have to build this model. Now you can observe that the build process is actually completed successfully. You can observe here. Now what you have to do? Then you have to open the control desk. Already I have kept it open. Now to go to File. You can go to the measurement, you can go to the project, and you can reload the variables. Then you have to press go online. Now you can see that various values. Now I have not run my plan, just the controller is active. Now it is actually generating the pulse required for the converters. So you can see that what I have done, I have taken the load current, I have taken the battery current. This is for visualization. And supercapacitor current, I have the PV power, voltage, current, VDC actual will be coming because I have not turned on my plant right now. This is the reference DC bus voltage. Battery voltage, you can observe it is the sensor is actually directly connected across the battery. You can see that we have got 24 volts over here, and the supercapacitor voltage is currently 25.8 volt. And this is the duty of the duty output of the PV MPPT system, and this is the duty of the battery and the supercapacitor converters. So after this, what we have done, we have taken the maximum power point voltage of the PV system to be 80 volt, and the maximum current is 8 ampere. So in this case, you can observe the maximum power is coming to be around 680 watt. So now I have given irradiation of 600 watt per meter square. Now I will be turning on my, I have connected now I am turning on the PV emulator. You can see in the other screen that there is a tracking of PV and PPT is going on over here. And we can see that we have reached the maximum power. Actually, I am operating my system at 600 watt per meter square, and the corresponding maximum power, PV power for this case is 360 watt. In the screen you can observe that the power output of the PV panel is coming as 360 watt here, and the PV voltage in this case is 72 volt, and the current output of the PV system is around 5 ampere. So if you multiply this one, you will be getting this value of 360 watt, and you can observe that the system is operating at the peak power. So the MPPT controller is working fine. Now I will be turning on my battery system. This is the switch for the battery, and this one is the MCB switch for the supercapacitor. You can observe that now the DC bus voltage is maintained constant at 48 volt. The bidirectional converter is maintaining the DC bus voltage at 48 volt, and you can see that the load power is 436 watt. Actually, the PV power, the power generated from the PV system is 360 watt. You can see that load power is 435 watt. Obviously, the PV power is not sufficient enough to match the load demand. So in this case, the battery is going to supply the power. So battery is going to operate in the discharging mode of operation. So you can see that battery is supplying a power of around 90 watt, and you can see that the battery reference current and the actual current are tracking perfectly. The battery current is around 3.7 ampere, which is matching completely with the battery reference current. Similarly, you can see, observe over here, the supercapacitor current is at 0 value. Now because we are operating in the steady state period, right? Now there is no transient is occurring. So in this case you can observe that, so the value is completely at 0. Now I will show you, I will decrease my irradiation. Sorry, I will increase the irradiation to 800 watt. Let's say I am increasing my irradiation to 800 watt per meter square. So you can observe that the power generated from the PV panel is now around 490 watt. So which is sufficient enough to meet the load demand of 435 watt. So what we are doing, obviously you can observe that the battery is now accumulating the excess power, or the 35 watt whatever is excess that is coming from the PV panel, it is getting accumulated. You can observe that the battery current is negative. So when the battery is getting charged, obviously the current is going to be negative. Here in this case you can observe that the DC bus voltage is maintained constant irrespective of the change in irradiation. Now suppose I am decreasing the irradiation. Okay, I will decrease the irradiation to, let's say, 500 watt per meter square. So you can see that the power generated from the PV system is 300 watt, as I have decreased the irradiation to 500 watt per meter square. So obviously the load battery is going to discharge more. You can see that battery current that is getting discharged is around 6 ampere. So in this manner the load balance is getting, means the power balance is happening actually. And you can see that the DC bus voltage is getting maintained at 48 volt. Now I will show the change in load. Now I am increasing the resistance of the load to 10 ohm. Previously it is 5 ohm. Now I am changing it to 10 ohm. So as soon as I increase the load resistance, obviously the load power is going to decrease. Right? So you can see that the power taken by the load is around 220 watt. Obviously in this case the generated power is excess, so the battery is accumulating or getting charged through the excess power. Again I will change my load resistance to 5 ohm. So you can see that again the same previous operation is happening. If you carefully observe, now I will do a load change again. You just carefully observe the supercapacitor current and the supercapacitor reference. You observe carefully just now. I am changing the load. You can see that there is a change in the supercapacitor current actually. So the transient is actually, when there is a transient, the supercapacitor is acting and it is giving the transient power to support the battery during that period, and then it is going down again to 0. So this is how you can operate your system using DSpace DS1103 digital controller. So now I will turn off the battery. Now the battery is, you can see the battery is disconnected from the system. You can now see that the DC bus voltage is not getting maintained at 48 volt. So now the DC bus voltage is at 42 volt. So basically it depends when battery is not connected. So obviously we cannot regulate the DC bus voltage. But there is a possibility that if the battery is connected to the system and the SOC of the battery is beyond 90%. So you cannot overcharge the battery. So what you have to do, the controller is going to automatically disconnect the battery. Means control algorithm is designed in such a manner that it will generate a zero reference current for the battery. So battery will not be physically connected, but the controller is going to disconnect it. So the battery actual current is going to be 0. In that case, what we will do, we have to switch the PV system to off MPPT mode. Now the buck converter of the PV system will be operating in the off MPPT mode. It will be regulating the battery. Sorry, it will be regulating the DC bus voltage at 48 volt. So I have turned off the PV system. So now I am going to show you. Just now I have shown you the experiment. Now I am going to show you how you will actually configure a new model. So let's say if you, in the MATLAB Simulink, if you create a new model, if you create a blank model, so before performing the experiment or modeling the complete control algorithm for the system, you have to make some changes in the configuration parameter if you are using a DSpace DS1103 digital controller. So for that I have made one document. So you can see that means the configuration that is present in the already preloaded in the MATLAB is actually unsuitable to use while doing the real-time implementation. So it is actually recommended to adapt some of the configuration changes. So for that, in the blank model, what you have to do, you have to just press Ctrl E, you have to press Ctrl E, you have to open the model configuration parameters. And first of all, for the simulation time will be kept at 0 and the stop time should be selected to be infinite. And then the solver option should be selected to fixed step, and you can use the OD4 or OD1, any of the solver you can use. Again you have to go through the additional step option. You have to fix a fixed step size. You have to select. Let's say I am putting PS variable. I will define it somewhere. You have to do this one. Then you have to go to all parameters. You have to type in the search pane block reduction optimization. See, you can see that in the category optimization we have a parameter block reduction is there. That will be actually checked. You have to uncheck this one and then you have to press apply. Another is there signal storage reuse. Signal storage reuse under the optimization category again will be checked. You have to uncheck this one. Another parameter is there. Conditional input branch execution will be there. Conditional input branch execution also you have to uncheck this one and you have to apply this one. Then you have to set the target. You have to set the target, you have to set the system target file. By default it will be git.tlc. So you have to change it to RTI1103.tlc. Real-time implementation using the DSpace DS1103, that's why it is RTI1103.tlc. You have to press apply. So this is the first step when you are doing real-time implementation. This is actually the first step. For this one I have actually made one document that can be shared with you. How you can interface your system with the DSpace controller. Any controller you can use, either it is DSpace DS1104 or it is 1103 or it is Microlab box DS1202. This one actually I have prepared. Here you can see I have kept all the details. One can edit this one and do modeling using the DSpace DS1103 digital controller. So this document I will share with the volunteers, they will share with all of you. So thank you for the patience hearing. So if you have any doubt you can ask. Any doubt? Any questions from the online participants? Shall we stop? Okay, thank you.
Welcome back to the GIAN course MHPDIMG 2024 conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. Now the presentation will be addressed by Professor Indrajit Sarkar and Mr. Vikas Verma, who is a PhD scholar under the guidance of Professor Indrajit Sarkar and Professor Monalisa Pattnaik, madam. So I request Indrajit Sarkar sir and to address you.
Okay, so let's start with this DAV demonstration. So now you already had a practical demonstration just over, so you can understand so how the things are different when you are doing simulation. When you are first what it is like this generally what happens when we start learning something, we write on the copy, and what we do is we just draw a single line to show a switch, power electronic switch. Then when we go to this simulation circuit, then we go one step ahead. But when we come to work with the hardware circuit, then we understand it is not that simple circuit as it looks like, but it comes with many associated things. So DAV converter, what I have presented, we have two H bridges, one high frequency transformer, and two DC sources, and two capacitors. So input side, output side. Now here when you see this, then we can see here there are so many components. So we have switches, power electronic switches. Okay, Vikas will explain the components. So we have one H bridge, input H bridge, another output H bridge, associated driver circuit, associated control circuit, and then the power supply that we never draw in our copy, never show in simulation circuit, is associated power supplies, and then we have the DSP microcontroller, and then we have the input and output capacitors, these sources, and this high frequency inductor and high frequency transformer. So this makes the complete thing, and then most importantly, we must be having these MCBs, okay, for protection purpose, and then we have load. And then there are voltage probes and current probes are also there. So Vikas will explain the components what are there, and then we'll execute this in SPS modulation scheme to see how the output will look like, and then in EPS also we'll see how the output will look like. So now it is over to Vikas, so you can explain now.
Thank you, sir. Today we are going to see how we can develop a DAV converter. So first of all, to develop the bridges, we need in DAV converter we have two active bridges. So to develop the bridges, I use a semicron IGBT module. In this module we can see there are two switches, connected in series. So we can see that when we look from here, this is the upper switch and this is the bottom switch, where this will be act as a one leg. So I use this one. We can see this three terminal is a character of upper switch, and one is a common as it is connected in series. One is a common terminal for upper switch emitter and bottom switch character, and two terminal is a emitter terminal of the IGBT module. So it work as a 600 volts. It work until 600 volts and 75 amps. So I use this IGBT module to develop my bridges. So before operating this IGBT, we need a proper gate drive circuit because we have to protect it, and we have to operate it in a proper way. So for that we use a semicron. This is the gate drive circuit. this gate drive circuit has different some features, like it has one primary input and two secondary input, outputs. These outputs are this one is for upper switch and another one is lower switch. It has a short circuit protection, like it will give a dead band, like without we can't so it will by its own self, like internally it give a dead band between the switching pulses to both the IGBT switches. So because of that, if there is at a time if both switches are getting on, there will be short circuit. So that thing it will give a protection by giving that propagation delay, providing between the two switching sequence of the both switches. And also it has a if there is a pulse which is less than 365 microseconds, it will not allow it. So it has that production short pulse detection will be there, so it will not allow it. And also it has a so this gate drive circuit input it requires 15 volts. So to on and off, like to on and off this IGBT modules, it will give 15 volts to the gate to make this IGBT on, and it will give -7 volts to make it off. So that everything, whatever the protection, if something error is there, this protection circuit, this gate drive circuit will off the circuit at that moment only. So it will not allow the switch to get short circuited. So this is the gate driver circuit. See, these are the power supplies to these ICs, where this IC will get a power supply from here, and also it has a and it will operate till 50 switching frequency of 50 kHz. So you can see, so it is under voltage. It has an under voltage protection. It has an under voltage protection. Like if it is 15, the required input voltage is 15 volts. If it is less than 15, like around 13.5, if it is less than 13.5 threshold voltage, it will get off. So that kind of under voltage protection is there in this, and also. Dynamic short circuit protection. As I told that it will not take any time, so it will instantaneously, when if it is a short circuit problem, it will instantaneously it will off the switch. So we can see the one main criteria is that it has a top bottom interlock dead time. The interlock dead time production is there, so it will give dead time between the two switches. And along with the dead time, it will give on propagation time delay is also there. See here, interlock dead time is around 3 to 4.3 microseconds. So, and also along with that 3 microsecond dead time, I will show you how it is giving. I will give a pulse with a 50% duty cycle. But after going to that switch sequence, that 50% will be reduced because of the dead time which is providing by this production this gate driver circuit. So, and again one thing I am using is that PWM board. So PWM board, this is a PWM board for to give the pulses from because of this microcontroller, it will generate 3 volts, but we need a 15 volt pulse. So for that we need a PWM board. So it will when we give the input to this, it will give to this circuit. So this one, this is these are the isolation. 67137. This is an isolation up. See, this is a photo isolation photo coupler, where it will provide the each isolation. This is for the 3 legs. This is for one leg, this is second leg and third leg. This is for 3 legs. It is controlling for the 3 giving the pulses to the 3 legs. So this is the isolation from this board. We are giving an isolation for this, and this is the NOT gate. Like as these are in 180 degrees phase shift, should be operated in 180 degrees phase shift. So there is an optocoupler. This is a NOT gate, where when the pulse high will come, it will make it as off. So we have 3 B dash. B is when high pulse will come here. B dash means it will be low pulse, like 180 degrees phase shift. It will make that one. This is the level shifter. So this is the level shifter. It will make a pulse into 15 volts. So how this chip it will be operated for at 5 volts, and this optocoupler this photocouplers, it will we have to provide 5 volts to operate it, and this NOT gate also we need 5 volts, and for this level shifter we need 15 volts. So this power supply for this is given by this Morrison power supplies. These are plus or minus 15 Morrison power supplies, and also we will get 5 volts. So these are the power supplies to give the power to this PWM board. So now, and also we need a snumper circuit. These are the snumper capacitors which are going to protect the short circuit valves, and these are the snumper capacitors. So now I am going to explain like how I am generating these pulses through this DSP microcontroller. So it is a this is a Texas instrument. It is a C2000 family, a Delfino family. It says TMS FT83790. It has 2 cores where we can use it individually, 2 cores. So each core the clock cycle is 100 MHz. So it has 169 multiplexer general purpose input output pins are there. Here we can see these are 169 pins. These are multiplexer, like we can use it as a PWM ports, and as a ADC and DAC ports also we can use it by giving a proper input signal to that. And it has a 12-bit mode for ADC signals. It will the ADC signals it will convert continuous signals into the discrete mode and digital signals. And we have 3 DAC modules also there. So each pin will give 3.3 volts. Like we have, if you want to give this is a main controller. So if you want to control the DAB converter, we have to provide a controlling circuit in this. So to each pin it will carry only 3.3 volts. If you give more than that, this pin will be get damaged. So for that we need a sensors like to step down it, to scale it properly, to give proper signals to it. And inside we can give, as it is working in a digital mode. So inside we will convert into a digital and from decimal to hexadecimal, and we can get an output through the DAC. So here I used CCS Studio, Code Composer Studio. So through this I use coding to generate the pulses. So we can see the EPWM, it has modules like EPWM, enhanced pulse width modulation. These are the main module that which we are going to use to generate the pulses to our driver circuits. So you can see now I will show you how I so I use like so I used EPWM1, EPWM2, EPWM3 and EPWM4. These are the 4 EPWM registers that I modules that I use to give the switching pulses to my gate drive circuit. So for that, so how we can know? So it is a GPIO pin. So how we can know which pin is the EPWM1, EPWM2? We have a data sheet. They provided a data sheet to us where we can see. See, we can see here, see EPWM, see it's a GPIO pin 40, GPIO pin 40. It will, GPIO 0, when we give a 0 to it, it will act as a GPIO pin. If we give 1, it will act as a GPIO 1A. Each pin, it has a, each EPWM model will act as 1A and 1B, where we can, at its same frequency, we can get a complementary signals through each with one EPWM model. So we are using EPWM1 and EPWM2, 3 and 4. So EPWM2A, it is at 38 pin, GPIO 02. So here we have to first give a command like to enable the EPWM model. So I gave EPWM1 as a 1. So when it is 1, the EPWM1 will be act. So for that we have to give that that GPIO 0 will be act as a EPWM, and EPWM2 is a GPIO 3. GPIO 2, it will be active when we give 1 logic, it will become a EPWM2A will be active. So if you want to use the EPWM3A, the GPIO 4, 36 pin, it will be act as a EPWM3A. So after I use one more, because we need 4 signals, because we are giving a phase shift between the legs and also between the two bridges. So for that I used 4 EPWM modules. So and also use EPWM4A, which is GPIO 06 is 80 pin. So I am using 80 pin 80 and also pin 40. pin 40 and pin 38 and pin 36. These 4 pins I am using to generate the pulse to give it to this driver circuit. So you can see that see these are the first I am doing SPS SPS control modulation technique. I am using SPS modulation technique. So we can see that we need what is the SPS. SP is a single phase shift. So single we should have a single phase shift. That is from primary to secondary bridge. We want a single phase shift. So for that single phase shift, that my first bridge it will be operate first switch will be on. When it is on, this it will be off. So we have 4 switches, right? So like this, we have one more module will be there. So this is switch 1. This is switch 2, switch 3 and switch 4. And switch 1 and switch 4 will be operated as on at one time, and switch 2 and 3 will be off at that time. So I am giving a pulses that 1 and 3 will be on, and 3 and 4 will be off when it is on. So and also this with same modules I am develop one more bridge where it has the phase shift. There will be a phase shift between the primary and secondary. So we have only one phase shift, because of that it is a single phase shift. So here you can see that I used GPIO 40, 38 and 36 and 80 pins to give the signal. See, we can see this is the for leg 1. So we can see this is for leg 1. See, this is for leg 1. So we can see there is a phase shift between the primary and the secondary. So this is the leg 1, and this is leg 2, this is the leg 3, and this is leg 4. This is for one active bridge, this is for second active bridge. So we can see there is a phase shift between this. I gave 40 degrees phase shift. So here we can't give directly 40 degrees phase shift in this program, like we have to convert into a digital signal. So I gave as 40 degrees for 40 degrees. The digital is 0511. So that it should be in hexadecimal. It is 16-bit register. So EPW is a 16-bit register. So we have to give in a hexadecimal mode. So I gave 0511. It is that 40 degree will be converted to digital as 0511. So and also I am operating. So at what frequency I should operate? So I took an operating frequency as 50 kilohertz. So I am working at a 15 kilohertz, 15 kilohertz. So I give like that 50. How we will decide that 15 kilohertz in this DSP module? That there is a module like so this is the okay. So this is EPW model signals and connection. This one EPW block diagram is here. So here our clock frequency is around EPW clock frequency 100 megahertz. So how we can make it as 100 megahertz into 15 kilohertz. So here clock prescaler is there. There is an high precision clock division. We have EPW clock. So we have to divide it. So for divide it, we have a clock prescaler is there. It will be scaled into our required frequency where we can get the 15 kilohertz. So there is a we can see the clock divider and high precision clock divisor are there. They both are there. So we can see. These are the clock div and HSP clock div. These are the two scalars where if you want 00 as a clock div, if you give 0, it will be 1. If you give clock HSP is equal to 0, it will be 1. So the formula for this is so here we can see the formula EPWM by HSP clock div into clock div. So this is the to decide the time based clock. So at what clock that EPW should operate. So this HSP clock div and clock div, these are the scaling bits where we can scale. So I use it at clock div 1 and div 1 and div 1. So I will use 1 and this one as a default. That clock div will be 1 and HSP clock div will be 2. So so the formula for this EPW clock is so so EPW clock div I use So from here we are getting a prescaler by using the EPWM clock and HSP clock. After that it is going to time-based counter. So this counter will at what count till what count it should go. So that is important. Like we should not go for infinity. So we should have a proper time counter till what count it should count. So this 16-bit time counter will be counted. So for after that we have to which kind of counter? There are 3 types of counters. The up counter is there, down counter is there, up down counter. So I am using here in my code I am using up down counter. See, TB count up down. So I am using up down counter. So but okay, we can get it in a triangular counter will become. So see this is the up counter, down counter, up down counter. So we can get like this. Okay, if we decide a TB counter, TB clock. So but how we can get the pulses? So we need a compare signal to compare that triangular. It will be decided this by the compare registers. So this compare registers it will decide like at what level. So at what level I have to do the compare because from it is going from 0 to TB PRT. So where I have to compare it. So for that there is a formula for that how at what compare value we have to give. See this is the formula. I will show an example. So compare A. So if I want a compare value, then you can see this is the compare value. So to get compare value, to compare duty cycle, we want to know which duty cycle should be operated. If I want to operate my duty cycle at 20 degrees, so it will be 100% minus 20% into TB PRT. As we by this formula we can find that TB clock is by pre-scaling the EPWM clock. So the TB clock will come, and also this is frequency of required. I want to operate at 20 kHz, so I want to this will be 20, and this will be regarding of prescaler. So 100 by here it is an example. If I want to operate in 20, 100 by 20 divided by 2. 1 by 2 is because it is up down counter. If it is only up or down, 1 by 2 will not be there. But 1 by 2 because of this up down counter. So 100 by 20 by 2. So it will be my TB PRT. So how I will get a compare value if I want to operate it as a 20% duty cycle. So 100 minus 20 into TB PRT. So I will get. So these are the digital values. We have to use the code. We have to give the digital. We can't give directly the values. Those are the digital values. So like that I decided my TB PRT and compare values. So how much? So I gave a point. I used 50 degrees duty cycle. So 0.5 into TB PRT. This is because 100 minus 50. So it is 50 degrees. So 0.5 into TB PRT. My TB PRT for 15 kHz is 1667. So I use it for this. So we can see here. So see these are 50 degrees. Means duty 50 on and 50 off. So the whole time is 100 T. This is the T on time and this is the T off time. So I use it as this is 50% duty cycle. So both my first leg is 50%, second leg 50%, third and fourth also 50%. But my phase shift, here the phase shift I gave 511. It is nothing but 40 degrees. So I am getting a 40 degrees phase shift here. You can see. So now we generate the pulses. So we have to check whether these pulses from here we are getting the pulses. So we have to check whether these pulses are going to EPWM, and after that it is giving to required voltage of required pulse to this IGBTs or not. So we will check that one. So I connected to, as I previously said, EPW 1A, 2A, 3A and 4A. 1A is at 40 pin, so I connected to 40 pin and ground. Then after it is 2A is a 38 pin, 3A is a 36 pin and 4A is a 80 pin. So I connected to this. So we have to give first to operate this this PWM board. We have to give 5 volts and 15 volts. So I will give with this. Okay. So we will check this one. So you can see the pulses coming with the duty cycle of 50. You can see duty cycle 50, 150. So yeah, pulses are coming. So what about the switch? The switch is getting the pulse 15 volts. Pulse or not? We have to check. So you can see that. Is it visible? Is it visible? So you can see that that's 15 and minus 7. Now see, you can see that each box is 5. So you can see that plus 15 and minus 7. So we are getting pulses to the switches. So now we will see our space is working or not. So as I previously told, this is the power supply which I am using. So this is the load resistance. So this is the high frequency transformer. As we know, DAB is the isolated converter. So these two bridges are connected with an isolation, the isolation transformer. This is a 20 kHz isolation transformer from 300 volts to 48, 300 volt to 48. Around the turns ratio is 6.25. And this is my external inductor. So you can see that the leakage inductor where the power transfer will be dependent upon this one. So there are different kind of formulas for each modulation, how to decide the inductor values. So So I am giving 100 volts. So I switching on the load, and I am switching on the, so you can see. So you can see, so this is the primary bridge voltage, this is secondary bridge voltage. You can see the phase shift here, so it is showing 24.7 phase shift, and this is the inductor current. So we can see this 99.8 volt, and the bridge volt 37.1 as the turns ratio, based on the turns ratio, and this is the inductor current. So our SPS is it is working with a phase shift. So now we will check with the EPS. So EPS, what will happen? It is like a square wave, but in EPS what we are giving is, we are giving EPS is extended phase shift. Extended means we are extending with another phase shift. So that extended phase shift will be within the bridge. So we between the two legs of the primary bridge, we are giving the phase shift. Now we are giving the equal, we are not giving any phase shift in the primary, but in EPS control that we are giving a phase shift. So we will generate in this and then we will check it. So we are giving a 20 degrees phase shift in the primary. It is the primary. So for 20 degrees, ours is 5 CA. We are running. So we will check it. So you can see. So you can see this is quasi square wave. You can see there is a phase shift between. See, it is not a square wave now. See, it is not a square wave now. So there is a phase shift between the legs. That's why it is coming as quasi square. See, there is a voltage becoming zero for some particular which will increase, because to reduce that one, to increase the efficiency. So this if we give the phase shift between the legs, so it will make a short there, and it will that bypass that back power flow through the diodes. It will freewheel it. So like that we can improve the efficiency. So we can see that there is a quasi square wave here. So EPS is also working. This inductor voltage in the secondary waveform, voltage waveform. So this is about SPS and EPS. Yeah, thank you. If you have any doubts, you can ask.